Let's talk now about 1D, okay? So I already drew this out ahead of time, but basically, let's now look at this problem where we have, like we did in separation of variables, we have some semi-infinite wall, or plane wall, meaning I have a firm boundary on one side, there's heat transfer happening at that boundary, but as far as the problem is concerned, the wall does not ever end, right? And obviously that's not like, it's an approximation, right? But it's a good approximation if there hasn't been enough time yet for that thermal wave to reach this other side of whatever this wall is. So for this problem, we're going to make the assumption that the time that has elapsed is low enough that whatever is on the other side hasn't been reached by the thermal wave. We're going to introduce this time varying ambient condition. Okay, so we have this up here says my ambient temperature is now a function of time. It's equal to T initial plus some constant times time. So we're just going to ramp up our temperature from the initial temperature to something higher according to beta, and then there's this convection heat transfer. So over on this surface over here, we have convection occurring, and the temperature of the ambient temperature is rising as a function of time. Okay, so our job then is to figure out how we can model this 1D problem, right? This 1D non-steady state problem as a function of time and as a function of position. Okay, so let's see. By the way, actually, this problem can be solved with separation of variables. We'll do it with Laplace just because we want to talk about that topic, and I think it's a good illustration of how to do it. Okay, so before we get into the actual Laplace method, let's do what we usually do. Let's come up with a good conceptual understanding of how we expect temperature to and heat transfer to behave as a function of time. Okay, so first let's say we are going to model this with a resistance network. Okay, so we have the ambient temperature over here. This is T as a function of time is equal to T initial plus beta time. And so that's the temperature here at this node. And then we have a convection resistance between that temperature and the surface. So that convection is R convection is equal to 1 over H bar times the area that's exposed there. So that's actually the cross-sectional area, AC, same as the surface area. Okay, and then we have another resistance. So think about a little bit what this resistance is going to be. So what's the resistance that's determining the heat transfer due to conduction into the body? Well, that's going to be approximately, so our conduction, approximately the thickness or the thermal wave penetration depth, which we'll call delta, sub T, divided by the conductivity times the cross-sectional area, right? So that's our conduction resistance. And then over here on the right-hand side, at the end of that resistance is our, whatever it was at the initial condition, the temperature at the initial condition, right? T initial. And let's go ahead and label this node TS as well. Okay, so if we want to just kind of figure out how heat transfer varies with time, just using this really conceptual approximate model, we can do that. So let's write out our heat transfer relationship here. So let's say, if you write this out, let's say Q dot into the surface is going to be equal to, let's see, did I miss? Yep. Okay, so writing this out would be Q dot is equal to T infinity minus T initial divided by R convection plus R conduction. Okay, noting that T infinity is a function of time, so let's actually sub back in what that function is. So that becomes T initial plus beta times time minus T initial divided by R convection plus R conduction. Okay, the two initials go away, so we're actually going to end up with Q dot is equal to beta times time over R convection plus R conduction. Okay. So progress, and then the last thing we want to do is include the resistance. So we have Q dot is equal to beta times time over 1 over h bar AC plus what's our relationship for delta t? If you remember back a couple lectures, it was 2 times the square root of alpha times time, and that's divided by k AC, right? So there's our really rough conceptual model of how heat transfers as a function of time. Right? And so you can see in the numerator is growing beta times time. And then the denominator, you have some fixed resistance plus something that's also a function of time. So what we actually have is a situation where there's kind of two time domains that are going to come into play here. So in one time domain, the convection resistance is really going to dominate. Right? In the other time domain, the conduction resistance is really going to dominate. So we could go through and actually kind of sketch out what we think this might look like. So let's see. Yeah, okay, so moving on here. So let's look at these different time domains. So in there's the short time domain and the long time. So let's actually do it like this. So short time and then the long time domain. So in the short time domain, let's see, this term over here, in the short time domain, that term becomes really small. And so we end up with heat transfer that looks something like this. It would be Q dot is equal to beta T over 1 over H bar AC. Okay, so that just is the same thing as H bar AC beta T. Okay, so that is proportional to time, proportional to time. So Q dot is proportional to time in this really short time domain. Now, as time grows, we have a slightly different condition. So we have Q dot is equal to still beta T in the numerator, but then it becomes 2 square root of alpha T over KAC. Okay, that can be rewritten as KAC beta T over 2 square root of alpha T. So that is proportional to T to the 0.5 power. T over square root of T. Right, so in the long time domain, the heat transfer rate kind of slows down, right? It's only growing with time to the 0.5 power, where in the short time domain is growing to in proportion to time. Yeah. Okay, so let's imagine that the variable t is just short enough where this becomes small relative to this. So when t is really small, then the convection is going to dominate. The convection resistance becomes much more important because they're in series, right? Than this, because it's very short time. As this gets bigger and bigger, this becomes the larger resistance. And then this kind of becomes small in comparison. So you have these kind of two different effects that are happening. Okay, we could also do kind of the same thing for surface temperature. So for surface temperature, that becomes Ts is equal to T initial plus R conduction times Q dot, which is the same thing as what? T initial plus 2 times the square root of alpha T over KAC H bar AC beta T. Okay, that's our temperature solution. So if we look through that a little carefully, we'd see this is proportional to T to the 1.5 power. Ts is proportional to T to the 1.5. So in the initial condition, in the initial phase of this problem, temperature of the surface is growing pretty quickly, I guess. Okay, and then in the later phase, we would have Ts is equal to, I'll just write it out, it's T initial plus, what is this? Becomes 2 times the square root of alpha T over KAC times KAC beta T. over 2 square root of alpha t. Okay, so then this simplifies down to just t initial plus beta t. So then time becomes proportional to just time, or temperature becomes proportional to just time. So the rate of temperature, surface temperature growth slows down over time. Okay, so this is all just to say we can have this really simple conceptual model that helps us understand what we think is going to happen, right? And in fact, if we look and plot it out, just using a really conceptual model, we can say here in our small time regime, just do it over here, in our small time regime, where time, this is a log scale, so time is less than, let's say, 1 second, 10 to the 0. That's when the convection resistance dominates. Okay, and then we can see for every, we said for every heat transfer in the short time domain, so the temperature or the heat transfer rate should grow in proportion with time. That means for every order of magnitude in time increase, we should have an order of magnitude in temperature increase. Okay, as we move to the long time domain, now it becomes every order of magnitude in time should correspond to sort of a half order of magnitude in heat transfer. And we see that, right? We see just, so this is kind of what we'd expect. If I sketched it out, it'd be 1 to 1 here, and then 1 to 0.5 here, right? And then you can do the same thing for temperature, just with the different values. So this is what we expect. This is what we see, what we think should happen just with our resistance model.